This episode is brought to you by Brilliant. One of the more interesting characteristics of a vehicle design is the sheer amount of energy that simply gets tossed away as heat. The obvious sources of these inefficiencies are the internal combustion engine, or even to a lesser degree, the electric motor and its battery system. But surprisingly, a vehicle's suspension system by design is a heat generator. In fact, a 2013 study found that a single shock absorber on a heavy vehicle driving over a rocky road at 30 kilometers an hour, or about 18.5 miles per hour, will dissipate approximately 32,000 joules of energy as heat every minute. To put that in perspective, that single shock absorber is dissipating enough energy to power a large home refrigerator. This is the story of how a simple kinematic problem evolved into a deceptively simple tube that contains a multi-purpose energy conversion device. Within a vehicle, a suspension system serves two primary functions as it supports the weight of the vehicle, isolating the vehicle body from road harshness, vibrations, and noise, and ensuring appropriate vehicle control through steering stability and handling characteristics. A shock absorber serves as a critical element in achieving these target goals. Fundamentally, a shock absorber is a mechanical or hydraulic device designed to slow down the dynamic motion of a vehicle's suspension in a highly metered manner. This is done by converting the kinetic energy of the suspension movement into dissipated heat. The vast majority of these devices function as a damper mechanism that resists motion via viscous or mechanical friction, making the term damper a more accurate representation of their function than shock absorber. The first conceptual attempts at a vehicle suspension system in the 16th century were quite literally suspension systems. Wagons and carriages hung the passenger-carrying body from leather straps attached to the chassis, isolating the body from the wheels and the chassis. By the mid-17th century, the earliest forms of a leaf spring began appearing on carriages in France and later migrated to England and Germany, and by 1804, Obadiah Elliott would be credited for the invention of the modern elliptical leaf spring. With the introduction of spring-based suspensions, a new problem became apparent. As a spring compresses and then releases its energy on a bump, it overshoots its equilibrium point, initiating a cycle of uncontrolled oscillation. For the most part, reducing this oscillation at lower speeds was inherent with leaf springs, as the friction generated between the stacked leaves as they rubbed against one another during flexion created a damping effect. However, the magnitude of the damping was uncontrolled and wildly inconsistent. It changed with wear, rust, and even humidity, making the vehicle's handling unpredictable. As vehicle speeds began to rise, a dedicated predictable damping device was needed. The first dedicated shock absorber concept to emerge were mechanical friction dampers called dry snubbers. While various methods were devised, the most prominent mechanical friction damper was the André-Hartford rotary friction disc damper. Originally invented by French cyclist J.M.M. Truffaut in 1898, the friction disc shock absorber, or Hartford shock, became common throughout the 1920s and 1930s. The mechanism consists of two arms connected by a bolt, with a friction element between them. One arm was attached to the vehicle's chassis, and the other to the axle. Damping force was applied by a large central bolt and spring that clamped a stack of friction discs made of leather, wood, or asbestos. While the design was adjustable by tightening or loosening the clamping bolt, it suffered from two major flaws. Because the damper relied on static friction, it resists any small initial movement, transmitting harshness from small bumps directly to the occupants. This characteristic is known as stiction. The damper also provided the same amount of resistance regardless of its travel speed. This velocity-independent damping is the opposite of an ideal damping profile, which requires soft, compliant damping at high velocities, and very firm, high resistance at low suspension velocities. This characteristic made the mechanical friction damper too harsh for comfort and too weak for vehicle control. Attempts at compensating for this velocity independence range from fitting rubber bump stops to the use of auxiliary springs, originally called shock absorbers, to disrupt oscillation of the primary spring. One notable attempt to add velocity dependence was the Gabriel Snubber. Invented by Claude H. Foster and introduced by the Gabriel Company in 1907, this unidirectional device was designed solely to damp the rebound stroke. It consisted of a canister housing bolted to the chassis, containing a coil spring and a friction belt mechanism. A heavy fabric belt was wound inside the housing and attached to the axle. When the vehicle hit a bump and the axle moved up, the belt retracted into the housing via the internal coil spring with minimal resistance. However, as the leaf spring attempted to rebound and the axle moved down, the internal mechanism engaged. A set of brass friction shoes or brake shoes expanded against the coil of the belt, creating friction that resists the belt's withdrawal. Later iterations of the snubber feature an anti-preloading brake shoe, a spring steel strip riveted to the belt. This prevented the device from engaging during very small movements, addressing the stiction issue inherent in friction dampers, and allowing for a smoother ride over bumps. Ultimately, the solution to this unwanted characteristic came from eliminating mechanical friction elements and transitioning to hydraulics. Though several concepts throughout the turn of the 20th century were explored, such as auxiliary spring dampers, French engineer Maurice Houdaille is credited with the development of the first practical hydraulic damper that was designed to be paired with the mainspring. Drawing on his experience developing hydraulic recoil mechanisms for French 75 field artillery during World War I, he adapted the idea of using fluid's resistance to flow to manage kinetic energy to vehicle suspension damping. Described as a shock-absorbing apparatus in his 1909 patent, Houdaille's rotary vane hydraulic damper, which became commercially known as the hydraulic lever arm shock absorber, used a lever arm that moved hydraulically damped vanes within a sealed unit containing a glycerine-based fluid. The fluid would resist sudden movement but still allow slow movement, creating velocity-dependent damping. By 1919, the Hu Engineering Corporation would be established in Buffalo, New York, to manufacture Houdaille's design for the U.S. market. While early versions were single-acting, rebound-only designs, by 1921, a double-acting version would be introduced with a more complex valve system that damped both compression and rebound strokes. For years, it remained a product of high-end luxury vehicles, but in 1927, Henry Ford announced that the Houdaille hydraulic shock absorber would be standard equipment on the upcoming Model A, ultimately leading to hydraulic dampers becoming a standard within the auto industry. While the lever arm style rotary damper dominated the 1920s and 1930s, its design required integration into the suspension by a linkage system and had packaging and travel limitations. It was also expensive to manufacture due to the tight tolerances required to seal the rotating vane against the cylinder walls. By the end of World War II, passenger vehicle design began to focus more on comfort and practicality while simultaneously reducing manufacturing costs. This trend led to the introduction of coil spring-based suspensions. Coil springs are more compact than leaf springs and transfer the load to a single point, which gives engineers more freedom in designing the vehicle's chassis while freeing up cabin and cargo space. They can also be designed to be lighter than leaf springs and are less expensive to manufacture. However, they did not integrate well with rotary dampers. To fully take advantage of coil springs, a damper with rectilinear motion was needed. While various forms of telescopic dampers have existed since 1905, none had seen much commercial success. The first production cars to feature them were the 1934 Hudson and Hudson Terraplane models. Monroe would introduce the first hydraulic unit in 1926 and refine the concept throughout the 1930s. By the post-World War II era, telescoping hydraulic dampers paired with coil springs would emerge as the dominant suspension configuration in passenger vehicles. The introduction of the Monroe-Matic damper in 1951 would solidify the concept as a true mass-market commodity. The twin-tube configuration quickly became a popular design for telescopic hydraulic dampers in the 1950s, and today it still remains the most common design for standard passenger vehicles. This design employs two nested tubes, a working inner pressure tube where a piston and a rod moves, and an outer reserve tube that surrounds the inner tube. It acts as a reservoir for excess oil and contains an airspace at the top. As the damper compresses, the piston rod moves inward, displacing oil. The oil is forced out the bottom of the inner tube through a base valve and into the outer reserve tube. As the fluid is forced through the orifices of the base valve, this resistance creates the damping force. This pressure differential also creates turbulence and shear stress within the fluid, generating heat, which is ultimately dissipated into the atmosphere and surrounding chassis components. On the rebound stroke, the rod withdraws, drawing back oil from the reserve tube into the inner tube through a check valve in the base valve. Simultaneously, the piston moves up through the oil in the inner tube, and valves on the piston head now provide the rebound damping resistance. The twin-tube damper has the distinct advantage over previous designs. By simply tuning the valving, engineers could easily achieve complex, digressive damping curves, where low-speed movement encounter higher resistance for stability, while high-speed movement experiences reduced resistance to allow the wheel to absorb the impact without transmitting shock to the chassis. This dual-valve system also allows for different damping rate curves for the compression and rebound stroke. While effective for general use, the basic twin-tube design had a critical flaw. Because the reserve tube contains both hydraulic oil and atmospheric air, under hard driving or rough roads, aeration can occur where the violent movement of the fluid can churn air into the oil, creating a frothy emulsion. Because foam created is compressible, the piston can move through it without generating hydraulic resistance. This creates fade, where the shock absorber loses its ability to control the spring, leading to a spongy, uncontrolled ride. It also drastically reduces the bulk modulus of the fluid, delaying the buildup of a pressure and causing a lag in kinematic response. This lag or hysteresis creates a dead zone where the suspension is effectively undamped for a fraction of a second as it transitions between compression and rebound stroke. In 1953, French engineer Christian Boursier de Carbon patented one of the first damper designs that solved the problem of aeration and fade by employing pressurized gas. Known as a high-pressure monotube gas damper, the design utilizes a single pressure tube that acts as both the cylinder and the outer shell. Inside, the tube is divided into two distinct chambers by a free-floating dividing piston. The upper section contains the fluid, working piston, and a rod, while the lower section contains high-pressure nitrogen gas, typically at around 200 to 360 psi. The floating piston provides a physical barrier between the gas and oil, making aeration physically impossible. As the piston rod enters the oil chamber during compression, the oil volume is displaced against the floating piston, which compresses the high-pressure gas chamber below it. With no air gap and the oil under high pressure, foaming and fade is eliminated. This results in consistent performance regardless of road roughness or temperature. The high static pressure also prevents cavitation of the oil on the low-pressure side of the piston, significantly reducing hysteresis and improving damping response. The single-wall design also allows the oil to transfer heat directly to the outer shell and the atmosphere, providing vastly superior cooling compared to twin-tube designs. Because the pressurized gas itself becomes part of the spring action of the suspension design, it compresses better over more minor bumps and quickly through bigger movements, improving control and response. Monotubes also have a larger surface area to spread the load, distributing pressure evenly over the entire damper, and there are no orientation restrictions when installing a monotube shock, though they are generally longer than twin-tube designs. In 1956, German suspension manufacturer Bilstein would license the de Carbon design, working with him to become the first to mass-produce monotube gas shocks and introducing them on production Mercedes-Benz vehicles of the late 1950s. While monotube dampers are conceptually simpler, in practice they require more precisely manufactured components and higher quality internal surface finishes to operate, making them inherently more costly than twin-tube designs. By the 1970s, manufacturers would derive a solution to aeration in twin-tube designs from the pressurized nitrogen used in monotube dampers. The solubility of a gas in a liquid is directly proportional to the partial pressure of that gas above the liquid. By pressurizing the gas within a damper, it prevents it from coming out of solution and forming bubbles. By introducing a low-pressure nitrogen charge of around 100 to 150 psi into the reserve tube of a standard twin-tube shock, the internal pressure becomes enough to minimize cavitation and foaming, although not as effectively as the high-pressure monotube separation. This hybrid approach offered a cost-effective improvement and quickly became the OEM standard for most passenger vehicles. As fade became less of an issue, the 1980s saw attention now focused on the compromise inherent in fixed valving dampers. This led to the development of the first position-sensitive and adjustable valving technologies that could react more dynamically to suspension action. The groove tube position-sensitive damping design introduced by Gabriel first achieved this by machining tapered grooves into the inner walls of the pressure tube. Under normal driving conditions, where the damper's piston stroke remained near the middle, hydraulic fluid could bypass the stiff piston valve by flowing through these grooves. This reduced resistance and provided a soft ride. During large suspension movement, such as in hard braking, cornering, or large bumps, the piston moves past the groove section into the smoother cylinder area. This forces all fluid through the piston valve, instantly stiffening the suspension. The concept of bypassing fluid would be expanded in the niche world of off-road racing. Known as bypass shocks, these units feature either internal channels or external tubes welded to the shock body that allow fluid to bypass the main piston at specific points in the stroke. By adjusting check valves in bypass pathways, the damping for different zones can be independently tuned, allowing for a soft suspension that can stiffen progressively as the suspension compresses to prevent bottoming out. More sophisticated variants can have multiple bypass circuits, allowing for even more tunability. To keep up with the capability of these higher performing dampers, the remote reservoir was introduced in order to increase the volume of hydraulic fluid and nitrogen gas for better heat dissipation and more suspension travel within a viable package. During the 1990s, the explosion of inexpensive and rugged microcontrollers would bring about a new era of software-based systems, and with this came a spectrum of sensors that monitor a vehicle's dynamics in real time, often operating in thousands of sample points per second. With this emerging capability, the concept of electronically adjusting damping in real time or semi-active damping became possible. One of the first successful implementations of this was developed by ZF Sachs as the continuous damping control. The system utilizes proportional solenoid valves integrated into the shock absorber that is commanded by an ECU that measures wheel speed, body acceleration, and steering angle. Based on the driving dynamics, the ECU sends a variable electrical current to the solenoid valve on the damper. The solenoid adjusts the size of the hydraulic orifice, with a wider opening reducing the pressure for a soft ride or a narrower opening restricting flow for a stiffer response. The system can switch from minimum to maximum damping force within milliseconds, allowing a vehicle to absorb a large bump and then immediately stiffen to control body roll in the subsequent corner. In 2002, Delphi, a division of General Motors, would introduce Magnetorheological on the Cadillac Seville STS, representing a fundamental shift in semi-active damping from mechanical valves to electromagnetics combined with Magnetorheological fluid. A Magnetorheological fluid consists of a carrier oil that is filled at 20 to 40% by volume with micron-sized ferromagnetic particles that are either round or ellipsoid. When subjected to a magnetic field, it greatly reduces apparent viscosity to the point of becoming a viscoelastic solid. The yield stress of the fluid when in its active state can be controlled very accurately by varying the magnetic field intensity, allowing the fluid's ability to transmit force to be controlled. In a Magnetorheological damper, the piston contains electromagnetic coils that, when energized, causes the ferromagnetic particles to line instantly into fibrous chains perpendicular to the flow direction, increasing the fluid's yield stress and dramatically increasing resistance to flow through the piston channels. Because there are no moving mechanical parts, the reaction time is less than 1 millisecond, allowing the damper to adjust multiple times during a single inch of suspension travel. This technology was later acquired by Beijing West Industries and is currently used by several manufacturers on higher-end models under the Magnetorheological name. A crucial element of electronically controlled damping systems are the algorithms that drive them. Two common models that are applied are Donald Carnop's skyhook model and the ground hook algorithm. Skyhook conceptualizes suspension control by tethering the vehicle's body to a stationary point in the sky. In practice, the system utilizes accelerometers to measure the absolute body velocity, instantly stiffening the fluid to hook the chassis in place or softening it to absorb impacts, thereby isolating passengers from roughness. The complementary ground hook algorithm, in contrast, attempts to pin the unsprung mass of the vehicle to the road. Modern electronic damper controllers continuously blend these complementary models to maximize comfort and handling, with a crucial element of their systematic design being a form of machine learning that attempts to predict which strategy to employ based on driving conditions and driver intent. The next evolution of the damper will likely be a more actively controlled design, with a broader spectrum of design goals, as vehicles become more heavily computerized and sensor-driven. While none of these advanced concepts have made it to commercial viability, the proliferation of powerful onboard computing and sensor fidelity and fusion in the recent decade has made existing damper control technology even more effective at predicting vehicle dynamics, leading to an ongoing transition to augmented vehicle handling characteristics completely synthesized in software, offering performance and modes of operation that are impossible with previous purely mechanical designs. The current state of dampers is a perfect example of how modern engineering is evolving. We aren't just dealing with steel and oil anymore. Algorithms, data, and logic are the new norm. And if you want to build the kind of intuition that lets you integrate software logic with real-world mechanical systems, you should check out Brilliant. Brilliant helps you excel in math, computer science, and engineering by helping you actually click with the concept, building on the idea that you are a problem solver. You just need the right way to unleash that potential. You won't find long lectures or memorization here. Instead, Brilliant guides you to aha moments through interactive, hands-on problem solving. They have also made massive updates, doubling the size of their content library and introducing personalized practice sets that adapt to you, ensuring you are always challenged at the right level. You can also be confident that you're learning the right way because Brilliant is handcrafted by an award-winning team of teachers, researchers, and professionals from MIT, Harvard, Google, and more, harnessing that expertise to design personalized practice sets just for you. And speaking of the logic behind mechanical systems, a great starting point I highly recommend is Brilliant's Algorithmic Thinking course. It helps you master the fundamentals of designing algorithms, a key skill for integrating software with mechanical engineering. With the new year coming up, a lot of us are thinking about self-improvement, and building a strong daily learning habit is a great way to kick off that journey. To start reaching your serious learning goals, go to brilliant.org/newmind or scan the QR code on the screen. That link will let you learn for free on Brilliant for a full 30 days. Brilliant is also giving my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything they have to offer.